Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 30, Organic Chemistry 1. Today we will continue on chapter 8, Structure, Synthesis and Reactions of Alkenes. Stability of alkene. To measure the stability of alkenes, scientists use heat of hydrogenation for that reason. So ethene plus hydrogen will give ethane, a reduction of the double bond from double bond to single bond, released 137 kilojoule per mole. So taking the alkene, double bond, hydrogen in presence of catalyst like platinum will transfer the double bond to a single bond and add 2 carbon hydrogen bonds plus heat. This energy we call it heat of hydrogenation. For the ethene it is 137 kilojoule per mole. For the mono substituted, like here in 1-hexene, release 126 kilojoule per mole. For the disubstituted in cis configuration, that's 119.3 kilojoule. Disubstituted in trans configuration, it's minus 115.95 kilojoule. If it's trans or it is geometrical, disubstituted, 1 disubstituted, it's almost the same energy. If it's tri-substituted, it is 111.35. If it's tetra-substituted, it's 108.85 kilojoule. You can see that the tetra-substituted is more stable, lower in energy than the mono-substituted, right? And that's called Zaitsev Rule. Zaitsev Rule. We'll come to it later on in this lecture. If it's mono-substituted, the energy released is almost the same for hexene, pentene, butene, for the same trend for disubstituted and tri-substituted and tetra-substituted. That's why we can use the heat of hydrogenation from simple molecule to predict the heat of hydrogenation for the more complex structure. In practice, we can use heat of hydrogenation to compare the stabilities of different alkenes as long as they hydrogenate to give alkenes of similar energies. Most of acyclic alkanes and unstrained cycloalkenes have similar energies, and we can use this approximation. For example, predict the energy difference between 2,3-dimethyl-butanene, 2,3-dimethyl-butanene, and 2,3-dimethylbutene. Which of these double bond isomers is more stable? Okay, this is digeminal disubstituted alkene. So approximation, it is minus, or energy released is 115.95 kilojoule per mole. For the 2,3-dimethylbutene, this is tetra-substituted. So the energy released is 108.85 kilojoule, which means that the tetrasubstituted is more stable by around 6 kilojoule per mole. Predict which member of each pair is more stable and by about how many kilojoule per mole. Cis hexa 2,4-diene or trans hexa 2,4-diene. Here we have cis, and for this double bond we have again cis. So we have two cis. Here we have two trans for this double bond, and for that double bond again trans. So we have two cis, two trans, 2 times 119.3 minus 2 times 115.95, difference about 7 kilojoule per mole for the trans more stable. Two methyl but1-ene or 3 methyl but1-ene. This is disubstituted, again geminal, and here is monosubstituted. So monosubstituted is 126, and for the disubstituted 115.95, which means that this one will be more stable with the disubstituted 2 methyl but1-ene more stable with about 10 kilojoule per mole. 2 methyl but1-ene or 2 methyl but2-ene. Here is disubstituted, and here is trisubstituted ene, right? So for the disubstituted 115.95, for the trisubstituted 111.35. So the trisubstituted will be more stable with about 4.6 kilojoule per mole. Zaitsev rule: more substituted double bonds are usually more stable. That is Zaitsev rule. You can see it in literature written this way or that way. It's Russian name anyway. Why does the stability of alkenes increase with substitution? As the alkyl group replacing the hydrogen, the more probability of the sigma CH and the CC bond of an alkyl carbon overlapping with the empty bi-star orbital of the double bond, mixing the full orbital of the sigma bond with the empty bi-star orbital results in a slightly lowering of energy. So here is alkene with CH. In this case we have double bond in here, and we have carbon adjacent to the double bond with CH bond. This CH bond has 2 electrons delocalized or mixed with the empty bi-star orbital of the carbon double bond carbon. We can imagine that the H is out, and here is double bond, and this break for this carbon to carry negative charge. So the CH sigma bond is aligned with a bi-star in here, and hyperconjugation features the delocalization of electrons It's no bond resonance. It's imaginary that these two electrons are mixed with the empty pi star. Okay? So lowering the energy and increase the stability. Cycloalkene stability. The presence of a ring only makes a difference in stability if there is a ring strain. Rings that are 5 carbons or larger easily accommodate double bond, and such systems behave like straight chain alkene. There is no ring strain. The ring strain in cyclopropene and cyclobutene is greater than that in the cyclopropane and cyclobutane. Thus, cyclopropene and cyclobutene are less stable than the analogous alkane. In cyclic alkane, cis isomer is generally more stable than that of the trans. The trans isomer is rarely observed unless a ring contains 10 or more carbons. So starting from 10 and above, you can see that you could have trans stable cycloalkene. Bredt's rule: a bridged bicyclic compound cannot have a double bond at the bridged head position unless one of the ring contains at least 8 carbons. Okay? So at least one of the ring in bicyclic should be 8 carbons, 8 member ring. Draw all the geometrical isomers and assign complete name using E and Z. Cyclodecene, 10-membered ring. If you draw the double bond in here, so it is cis, and the two groups here are on the same direction, so it is Z. You can have the double bond in here, and the two R groups are trans, so it's E. All what I did, I took the structure to 3D, and as you can see, and put the molecule in the minimum energy, and here we have the cis isomer. Okay, in here again for the trans isomer, acceptable, so both do exist and show stability. Cyclodeca 1,5 diene, cyclodeca 1,5 diene. We can have 1Z5Z, cis, ZZ, 1E 5E, trans, and then 1Z 5E. Again, building up, we have here double bond, we have here double bond, here we have here double bonds, trans, we have here trans, trans, here we have cis, and the other one here we have trans. Explain why each of the following alkenes is stable or unstable. Explain why each of the following alkenes is stable or unstable. 1,2-dimethyl cyclopentene, trans 1,2-dimethyl cyclopentene, trans 3,4-dimethyl cyclopentene, trans 1,2-dimethyl cyclodecene, and these compounds drawn. For the first one, 1,2-dimethyl cyclopentene, stable, but with little strain. It's 5-member ring. It's in the cis geometry and acceptable. Trans 1,2-dimethyl benzene. You can draw trans for 5-member ring, so does not exist. The ring must be 8 or more to accommodate trans double bond. What about trans 3,4-dimethyl cyclopentene? The trans here belong to the dimethyl, these two dimethyl. This should be 1, 2, 3, 4. So we are talking about trans 3,4-dimethyl. Yes, of course, stable, but with little strain. It's 5-member ring. The trans refer to the position of the two methyl groups. For trans 1,2-dimethyl cyclodecene, it is stable. The double bond is in 10-member ring. So again, you can see double bond here. Trans. Here is a double bond. Methyl trans. Okay. Again, you take this structure to 3D, minimize the energy using MM2 software and find out if it exists or not. The compound is stable. For this compound, it is unstable. Why? Taking again, draw the structure, put it in a 3D, you can clearly find the structure would like to be like in a boat cis configuration. Cis, and here is cis. What about this compound? Bicyclo 2,2-oct-1,2-ene. Stable since double bond is not at bridgehead. Bridgehead, it's here, this one or that one. That's bridgehead. Okay? So it's here in 6-member ring, it's not in bridgehead. So it's stable. For this one, again, this is a bridgehead. Okay? If it's bridgehead, it has to be 8 and more. Unstable, violate Bredt's rule. A bridge bicyclo compound cannot have a double bond at bridgehead position unless the ring contains at least 8 carbon atoms. Bicyclo 4,2,1 nonene at one position, it's bridged position, but here we have 8-member ring. So it is stable, double bond at the bridge in 8-member ring, acceptable. Here is a double bond. For this one, it's unstable. It is the double bond at bridged head, but the largest ring is 7-member ring, and we need at least 8-member ring to get stable alkene. Physical properties of alkenes. Boiling point, densities, and solubilities. The boiling point of each alkene is very similar to that of the alkane, with the same number of carbon atoms. In each case, the alkene has a boiling point which is a small number of degrees lower than the corresponding alkane. So the alkene is a little bit lower than the corresponding alkane. The only attraction involved is our van der Waals dispersion force. And this depends on the shape of the molecule and the number of electrons it contains. Like the alkane, increased branch leads to greater volatility and lower the boiling points. Here we have 1 pentene, boiling point is -6. We increase the branch with the same number of carbon to methyl prop 1-ene, we get lower boiling point. It's -7 degrees Celsius. Also, like alkenes, alkenes have density lower than 1. So it is less dense than water. So it's always you find it in the upper layer. Like alkenes, alkene are relatively nonpolar. They are insoluble in water. Alkenes are insoluble in water, but soluble in nonpolar solvent such as hexane, gasoline, halogenated solvents, and ethers. Alkenes tend to be slightly more polar than alkane for 2 reasons. The more weakly held electrons in the pi bond are more polarizable, contributing to the instantaneous dipole moment. The vinylic bond tend to be slightly polar, contributing to a permanent dipole moment. Alkyl group are slightly electron donating. CH3 is electron donating, the alkyl groups. Okay, so we have here dipole. In the cis, the 2 methyl group are giving electron away, and we can see that it has dipole. In the trans, has no dipole because this is pushing this way and the methyl group pushing the other way around, making the dipole moment equal to 0. So alkyl group are slightly electron donating toward the double bond, helping to stabilize it. This donation slightly polarizes the vinylic bond with a small partial positive charge on the alkyl group and small negative charge on the double bond carbon atom. For each pair of compounds, predict the one with higher boiling point. Which compounds have 0 dipole moment? Cis-1,2-dichloroethene or cis-1,2-dibromoethene? Of course, cis-1,2-dichloroethene should have high boiling point because it's the Br has higher atomic weight, so the compound cis-1,2-dibromoethane will have higher molecular weight. Okay, cis or trans 2,3-dichloropentene. For the cis 2,3-dichloroputene, we will find the dipole moment. Methyl is pushing this way, the other methyl that's the same, chlorine this way, so it has a total dipole moment this way higher than 0. In the trans 2,3-dichloroputene, we'll find the methyl in one direction, the other methyl oppose this direction. The same for chlor, this is up and this is down. So deleting one another, canceling one another, and the dipole moment will be equal to 0. 1,2-dichlorocyclohexene should has higher boiling point than cyclohexene. Again, this compound 1,2-dichlorocyclohexene has dipole and higher molecular weight. So the boiling point will be higher than cyclohexene because the molecular weight is higher. Here it has higher dipole moment than the cyclohexene. Once again, here we have two methyl pushing this way. So it will have dipole, but this one is higher because it has the methyl as well as the chloro effect. See you in the coming lecture. Bye-bye.